The faint young sun paradox is an intriguing puzzle from our planet's early history. Billions of years ago, the sun was about 70% as bright as it is today, which means that, in theory, Earth should have been frozen over. Yet geological evidence shows that liquid water, and even early life, existed. How did early Earth stay warm when the sun was so faint? One major explanation lies in the composition of Earth's atmosphere. Scientists believe that higher levels of greenhouse gases, such as carbon dioxide and methane, created a much stronger greenhouse effect. This effect trapped more of the sun's heat, keeping the planet warm despite the lower solar output. For example, volcanic activity during that time could have released large amounts of CO2, while early microbial life might have produced methane. These gases would have formed a thermal blanket around the planet, preventing it from cooling too quickly. Another possibility involves the planet's surface characteristics. Early Earth may have had a lower albedo, meaning it reflected less sunlight back into space. With more of the sun's rays absorbed by the surface rather than bouncing away, more energy would be retained as heat. Imagine a dark, forested area that absorbs sunlight compared to a snowy field that reflects it. In the early days of Earth, vast oceans and minimal ice cover could have contributed to a darker surface overall, further boosting the warming effect. There are also ideas that changes in the sun's output itself might have been different from what we expect, or that additional energy sources played a role. Some theories suggest that the young sun might have been more variable, or that other factors like intense cosmic radiation contributed extra energy. However, the prevailing view focuses on the powerful greenhouse effect and the planet's albedo. So why is solving the faint young sun paradox important? Understanding how early Earth maintained a warm climate despite a dimmer sun not only helps us piece together our planet's history, but also provides clues about the conditions needed for life. It also informs our search for habitable worlds around other stars, where a similar balance might be at work. In summary, the faint young sun paradox challenges our expectations by showing that early Earth was warm enough for liquid water and life, even though the sun was much weaker. The solution most supported by evidence points to a dense greenhouse gas-rich atmosphere and a lower albedo, both of which helped trap enough heat to sustain a temperate climate. Could this understanding also guide us in exploring other planets where life might exist under seemingly harsh conditions? The ongoing research continues to shed light on this fascinating chapter of Earth's history. The faint young sun paradox refers to the scientific puzzle of how early Earth maintained liquid water and warm conditions, despite the sun emitting only about 70% of its current energy, billions of years ago. A weaker sun would normally suggest a frozen Earth, yet geological evidence shows that our planet was not entirely ice-covered. Scientists propose that factors such as atmospheric composition played a critical role in trapping heat and sustaining life, challenging our understanding of climate systems and planetary evolution. Early Earth, though receiving less solar energy, still had warm oceans and a climate that supported early life forms. It's like trying to keep your house warm on a cold day with a small heater. You need extra insulation or other heat trapping methods to maintain a comfortable temperature. One explanation for the paradox is that high concentrations of greenhouse gases, such as carbon dioxide and methane, created a thick atmosphere that trapped heat. These gases would have enhanced the natural greenhouse effect, warming the planet despite the faint young sun, and could compensate for the lower solar output by retaining more heat in the atmosphere. Geological evidence suggests that early Earth's atmosphere had much higher levels of carbon dioxide and methane than today, contributing to a strong greenhouse effect. It's like wrapping yourself in multiple layers of a blanket on a cold night. The extra layers help you stay warm, even if the external temperature is very low. The composition of early Earth's atmosphere was vastly different from today, with a predominance of gases that contributed to a strong greenhouse effect. The lack of free oxygen and the abundance of volcanic gases could have created an environment that efficiently trapped heat, allowing the planet to retain enough warmth for liquid water to exist. Scientists have reconstructed atmospheric models indicating that early Earth's thick, greenhouse gas-rich atmosphere was capable of maintaining liquid water despite receiving less solar energy. It's like a greenhouse that stays warm inside during winter because its glass walls trap heat from the sun even if the sun is not very strong. The enclosed environment remains warm. Earth's albedo is a measure of how much sunlight is reflected back into space, and a lower albedo means more solar energy is absorbed. In early Earth, factors such as a lack of widespread ice cover and different land vegetation could have reduced the albedo, allowing more heat to be retained so that even a fainter sun could deliver enough energy to keep the planet warm. If early Earth had darker surfaces due to volcanic rock and sparse ice, it would absorb more sunlight and retain more warmth. It's like wearing dark clothing on a sunny day. You absorb more heat compared to wearing white, which reflects the light. Methane is a potent greenhouse gas that can significantly enhance the warming effect of an atmosphere, even in small concentrations. In early Earth, biological and geological processes could have produced abundant methane, which would have contributed to the greenhouse effect by trapping additional heat. Microbial life on early Earth might have generated methane as a byproduct, adding to the greenhouse effect and aiding in warming the atmosphere. It's like adding a powerful spice to a dish. The small amount has a large impact on the overall flavor, just as methane greatly influences the temperature. Intense volcanic activity in early Earth released large amounts of greenhouse gases into the atmosphere, further enhancing the greenhouse effect. Volcanic eruptions emit carbon dioxide, methane, and water vapor, all of which trap heat, and this continuous supply of greenhouse gases could have maintained a warm climate despite the faint young sun. Periods of heightened volcanic eruptions in early Earth likely contributed to sustained warming, counteracting the lower solar output. It's like using a space heater in a cold room. The additional heat source helps maintain a warm temperature even when the main heater is not very strong. Oceans have a high heat capacity, meaning they can absorb, store, and slowly release heat over time. In early Earth, large bodies of water would have absorbed the available solar energy and moderated temperature fluctuations, with the gradual release of stored heat from the oceans contributing to maintaining a warm environment conducive to life. Evidence suggests that early oceans acted as a thermal reservoir, slowly releasing heat to the atmosphere and stabilizing global temperatures. It's like a hot water bottle that retains heat and gradually warms you throughout the night, keeping you comfortable even in a cool room. The conditions created by a strong greenhouse effect and efficient heat absorption were critical for maintaining liquid water and a habitable climate on early Earth. These conditions allowed life to emerge and evolve in an environment that was warmer than what the faint young sun would suggest, as the interplay between atmospheric composition, oceanic heat storage, and volcanic activity set the stage for biological evolution. Geochemical evidence shows that despite receiving less solar energy, early Earth maintained a climate that supported the evolution of microbial life. It's like a greenhouse that creates the perfect growing conditions for plants, even during a cold season. The carefully controlled environment nurtures life. Ongoing research continues to refine our understanding of the factors that resolved the faint young sun paradox. Scientists use advanced computer models and geological data to simulate early Earth conditions and test different hypotheses, a process that not only illuminates the past but also enhances our understanding of climate dynamics and planetary habitability. Unraveling this paradox provides insights into how life might exist on other planets with varying solar outputs. Researchers are using simulation models to recreate early Earth scenarios, testing how different greenhouse gas levels and ocean conditions could have maintained a warm climate. It's like experimenting with different recipes to bake the perfect cake. The adjustments in ingredients and methods reveal how each component contributes to the final result.